Hey guys, so this is going to be our last bit of new information, yay, for your optics test, which I'm thinking might be, I want it to be on Thursday. We'll see. Maybe it'll get pushed to Friday if you're lucky, because that's the day before spring break. I don't know, we'll see. But this is the last bit of information, new information. We've talked about reflection, refraction, diffraction, and now this is interference, those are the four main properties of waves. And this is interference. Because we talked a little bit about interference when we talked about diffraction and how waves interfere to produce, or diffraction creates interference patterns. But this is interference with thin films. So very thin films, thin layers of material, and how interference patterns can create different colors. Okay, when we're talking about light, which is what we're going to focus on now. So you should have this in front of you. So once again, it's just kind of fill-in notes. Okay, so recall when a wave hits a rigid barrier. We've talked about that a couple weeks ago. When a wave hits a rigid barrier, when the wave reflects off that rigid barrier, it comes back 180 degrees out of phase. Okay, so here we have our barrier. Here we have our wave coming down to hit that barrier. Okay, and as that wave reflects back, it's going to reflect back out of phase. Okay, 180 degrees out of phase. Okay, and so basically what does that have to do with light? Well, this is what happens. This 180 degree phase reversal is what happens when light travels from a less dense medium, meaning a medium with lower index of refraction, into a more dense medium, higher index of refraction. And when this happens, we call this a phase reversal, okay? Because the phase at which it comes in, if it comes in as a crest, it leaves as a trough. It reverses. The waves being reflected back can then interfere with the waves that are hitting the barrier between the mediums that come next. Basically, between the mediums, the next waves, okay? So basically, if you have a crest come in and it hits a layer that has a higher index of refraction, then the wave that comes back is going to interfere with the waves that are being propagated toward it. Okay, this interference can affect what type of light you see reflected off of a surface. Okay, so this type of interference is what causes rainbow patterns on bubbles or oil slicks on water. So if you've ever, after a rain, you look in the parking lot, everything looks all rainbowy. Okay, those are basically thin film interference patterns that you're seeing. Some wavelengths of light, remember, that corresponds to different colors, get canceled out, which is destructive interference. And some of those wavelengths get reinforced. This is constructive interference. Okay, so phase reversals are basically one part of it. Okay, so if I hit a barrier, say I'm in air, and my thin film, this is my thin film right here. Okay, my thin film. Say it has an index of refraction of, say, 1.5. Then as light hits that barrier between air and my thin film, then I'm going to end up with a phase reversal. And we're going to denote that with a PR, P dot R dot. Okay, a little phase reversal. Okay. All right. So we're going to focus on this type of interference and how it relates to thin films or thin layers of a certain medium, like a bubble on water or oil on water. Okay. The thickness of this thin layer, so how thick the thin layer is, along with how many phase reversals are present on the boundaries of that thin layer and the mediums around it, will tell us how light and what type of light we will see reflected off of the surface of the thin layer. Okay. So just like anything else, here is the general equation for thin film interference. Okay, 2nt equals m lambda. All right, so n is your index of refraction of your thin film. Okay, t is the thickness of the thin film. M is your order number, which we'll talk about what that means in just a second. It's going to be usually 1, 0, or 1. Okay, basically whatever gives the lowest value without being 0. Without making the whole equation 0. Okay, and then this is the wavelength of light, obviously, wavelength of light that's hitting, or that you want to find the pattern for. Okay, so an important part of understanding what wavelengths will be reflected, remember reflection, if you see something reflected off of a thin film, you're seeing constructive interference happening. So if I see a reddish pattern on some oil that is on a parking lot, on the ground of a parking lot, and it's on water and it looks really like it looks red or it looks blue, then that's the wavelength red, the wavelength of red that I'm seeing reflected off of that surface. So that's an area of constructive interference. Okay, if you have wavelengths that you don't see and they're being absorbed, okay, that's an area of destructive interference. Okay, so an important part of understanding what's going to be reflected or absorbed is counting how many phase reversals are present for that given thin film. Okay, so this is how you know what kind of phase reversals are happening. Whoops, didn't mean to do that. Okay, so a keynote here, this is important. Okay, a phase reversal, you know there's a phase reversal when light goes from a less dense to a more dense medium, basically lower to higher index of refraction. So let me just give you an example. Let's say I have a really thin film of water. This is water, N equal to 1.33 in air. This is N equal to 1, and this is water. And this is now air again. So it's like a thin film of water in air. Okay, and it's bounded by air on both sides. Let's pretend like we're on the space shuttle and there's no gravity and there's water that's just this little thin film that's floating around on the space station. Then let's talk about how many phase reversals we have. So you're going to have light reflected off the top. That's a boundary. And then you're also going to have light reflected off of the bottom of the thin film. That's another boundary. So let's see. The first one, we're going from N equal to 1 to N equal 1.33. Is that a phase reversal? Are we going from lower to higher? Yes, we are. Ding, ding, ding. Phase reversal. Okay. What about this guy? N 1.33 to 1. Is that a phase reversal? Nope. No phase reversal. Okay. All right. So the number of phase reversals we have here is 1. We have 1 phase reversal in this problem right here. I'll give you another example. Let's say I have a thin film made of bubbles. And air's on one side, and then there's water on the bottom. So it's like a bubble that's like sitting on water. It's like real thin film of bubbles. This is N equal to 1. Let's say bubbles are N equal to 1.25. I have no idea if that's the case or not. I'm making it up. And this water is 1.33. Okay. All right. So let's see how many phase reversals we have, because we're going to have light reflected off the top of the thin film and the bottom. It's always that way. Always that way. Okay. We have to figure out how many phase reversals we have. Okay. So let's see. What about between the first one, air and bubbles? Yep, we sure do. We're going from lower to higher index of refraction. So we have a phase reversal here. What about here? We're going from lower to higher index of refraction here too. So we have a phase reversal here as well. 2 phase reversals. So the number of phase reversals for this one is 2. Okay, you guys getting the hang of this? All right. All right. Okay, so on your back of your sheet. So the thin film equation that's on the previous page and this chart that I'm about to share with you are not on your equation sheets. I have no idea why the powers that be at the AP exam decided not to put the thin film equation on there. but they did not. So you have to know it, and you have to memorize it. I'm terribly sorry. You're going to be memorizing all of your equations anyway, right? Because you have an equations quiz on Friday, or you would have had it if you're going to watch this after Friday. So you have to memorize all these anyway. So anyway, so how do you know when you have constructive or destructive interference with, like, depending on how many phase reversals you have, you know, that sort of thing. Okay, here's your equations, okay? Basically, if you have one phase reversal, okay, then think of it like this. If you're looking at one phase reversal and it's wanting to know what is the reflected wavelength that you're seeing, what is the, you know, the brightest color you're seeing, what's that reflected wavelength? That's constructive interference. You're going to use this equation, and usually it talks about the thinnest film possible, like what is the thinnest film possible that creates that sort of interference. Then you're going to use m equal to 0, because you want this to be the lowest number possible. Lowest number possible. Lowest. Okay, but let's say, okay, what wavelength is going to get canceled out? What wavelength is going to get absorbed and you won't be able to see it? That's destructive interference. Okay, and I want to know the thinnest film possible. You're going to use this equation, and so m is going to have to equal 1 in this case. Okay, because if it was equal to 0, it's going to cancel out your whole equation, and that's lame. So if you have 0 or 2 phase reversals, it's just flipped. Okay, all right, let's do an example. All right, here's our example. Calculate the minimum thickness of a soap bubble film that is on top of a glass slide with, so it's a film of soap on top of glass. So let's draw what that looks like. Here's our bubble, soap film, n equal to 1.33, and it's on top of glass, which n is equal to 1.5, and that's in free space, so it means it's in air. You're just, you know, it's just n equal to 1. Free space, n equal to 1. Okay? It says calculate the minimum thickness of the soap bubble film. Okay? Calculate the minimum thickness that will result in constructive interference in the reflected light if the film is illuminated by light with a wavelength of 602 nanometers. So basically it wants to know what is the thickness of this film, okay? The very first thing you have to do is count phase reversals. Because if you don't do that, how are you going to know what equations to use from the chart? Okay, so let's take a look. Light's going to get reflected off the top, and light's going to get reflected off the bottom of the film. Okay, so at the top of the film, let's see, do we have a phase reversal? We're going from 1 to 1.33. Yes, we have a phase reversal. What about 1.33 to 1.5? Okay, yep, we have a phase reversal there too. Remember, by definition, phase reversal happens when you go from less dense to more dense. Lower index of refraction to higher index of refraction. So we have 2 phase reversals. And we want to know the thickness, the minimum thickness that's going to result in constructive interference. So let's look, guys. We got 2 phase reversals on our chart. We're looking for constructive interference. So this is the equation we're going to use. Okay, 2 phase reversals, constructive interference. This is the equation. Okay, 2nt equals m lambda. Okay, so it said minimum thickness, so I want to use the lowest order number, okay, which is 1. Okay, which is, guys, 99 times out of 100, this is going to be 1 in this equation, 0 in that equation, like all the time. Okay, in terms of your m. Okay, all right, so this is going to be 2 times, it's always n, remember, is always the index of refraction of your film, so that's 1.33 times t equals 1 times lambda, 602 times 10 to the minus 9th meters. Okay, and you get a thickness of 226 nanometers. That's very thin, right? All of these thin films, guys, when we say thin, we don't mean like a millimeter, we mean like nanometers. Okay, so there we go. Trying to think if I'm forgetting anything. Nope, we're good.